Section 13.8, extrema of functions in two variables. Okay, so a lot of this is just going to extend right out of what we did in one dimension in Calc 1. The extreme value theorem is going to be extended. The extrema is going to be extended. The only difference is instead of it being on an interval, it's going to be on a disk or in a region, right? So let's go ahead and start talking about these things. So first of all, let's start with the extreme value theorem. Okay, so this is going to be extended into functions of two variables. So we've got f. So we're going to let f be a continuous function of two variables, x and y, defined on a closed, bounded region R in the xy plane. Okay, so to give you an idea of what we're looking at here, we have got f is a function of two variables, right? So I've got some surface f, whatever that might look like, hanging out in 3 dimensions. And it is defined on some region R in the xy plane. So whatever that region might be, maybe it's this region, this disk here. So it's closed and bounded. And I can come up here and see that this is defined on this entire region, right? And so it's probably misshapen a little bit because of that, but if I were to cast shadow straight down, it would come straight down onto the region R below it, okay? Just pretend all that stops on R right there, okay? So that's what that's saying. Then 1, there is at least one point in R at which f takes on a minimum value. At least one point in R where f takes on a minimum value, and 2, there's at least one point where it takes on a maximum value. 2, there is at least one point in R where f takes on a maximum value. And by min and max, we just mean that it's going to be greater than all the other values of f for that region, for all the xy points in that region R. Okay. Okay, so we have relative extrema. So those are exactly what they were in Calc 1, just extended to 3 dimensions, of course. So a relative maximum means it is greater than any of the points in the region immediately around it, and a relative minimum is it's smaller than all of the other points on the surface right around it in that region. Okay, so let's go ahead and define that. So relative extrema. Okay, let f be a function defined on region R containing the point x naught, y naught. Okay. Then 1, the function f has a relative minimum so a relative min at x naught, y naught if f of xy is greater than or equal to f of x naught, y naught for all xy in an open disk containing x naught, y naught. For all xy in an open disk containing x naught, y naught. Okay. Likewise, it has a relative max. So f has a relative max, relative max at x naught, y naught if f of xy is less than or equal to f of x naught, y naught. So not there. Okay, x naught, y naught for all xy in an open disk containing x naught, y naught. And as in Calculus 1, to locate a relative extrema, we are going to look for places where the derivative, and I'm doing that with air quotes, the derivative is equal to 0. The only problem is we don't have a derivative when we're dealing with multiple variables, but we do have a gradient, which contains the partials of each of the variables, the partial of the function with respect to each of the variables. So that's what we're going to do next. To find the relative extrema, there we go, we are going to look for critical points. Look for the critical points. Critical points, okay, I will abbreviate that CP. The critical points where the gradient of our function f, the gradient is equal to the 0 vector. Okay, so the definition of a critical point. Let's go ahead and write that down. Okay, so we have f defined on an open region R containing the point x naught, y naught. That point is a critical point if, I should be writing all this down, shouldn't I? Let f be defined on an open region R containing the point x naught, y naught, containing x naught, y naught, then the point x naught, y naught is a critical point if either one of these are true. Number one, the partials with respect to x and y are both 0. The plugged in at x naught, y naught is equal to 0, and fy of x naught, y naught is equal to 0. Okay, meaning the gradient is equal to 0. Okay, or 2, if one of those partials does not exist. Okay, so if, just like what we saw in Calculus 1, if the derivative, in this case the gradient, was equal to 0, it was a critical point, or if that derivative did not exist, in this case either of the partials, if those do not exist, we have a critical point. All right, and it is a theorem in our book. I'm not going to bother to write it down, but relative extrema can only occur at critical points. If there is no critical point there, it can't be a relative extrema, because by nature of it being a relative extreme, it's going to generate a critical point. So it's, if you're going to look for relative extrema, it's going to occur at a critical point, period. Okay, so let's do an example where we actually find a critical point. So example, find any critical points for f of xy equal to 2x cubed, squared, plus y squared plus 8x minus 6y plus 20. Wow, try that again. Plus 20, there we go. Okay, so if we're going to do that, we need to know what are the partials. So the partial with respect to x is going to be 4x plus 8. The partial with respect to y is going to be 2y minus 6. Okay. Looking at these, we need to determine if either of them have a point where they do not exist. And these are both polynomials, so they exist for all values of x, y. So the gradient of f is going to exist for all values x, y. Okay, because they are a polynomial. So then the only other way I'll have a critical point is if the gradient of f is equal to the 0 vector, or in other words, if fx is equal to 0 and fy is equal to 0. So we set both of those equal to 0 and solve. Now, this is going to be a very straightforward solve, right? Because The first equation has only x, the second equation has only y. If we had a situation where both equations contained x's and y's, we would just be solving a system of equations. Okay, but this one's pretty straightforward. So this is x equal to -2, y equal to +3. So we have a critical point at -2, 3. So there's our critical point. We want to know, is this thing a minimum or a maximum, though? Like, what's the point knowing if you have an extrema if you don't know what kind of extrema, right? So we need to know, is this a minimum? Is this a maximum? What's going on here? Well, there's a couple of different ways you can do it. For us on this one, what I would say is, let's go ahead and take our function, complete the squares, find out what kind of quadric surfaces we have, and then figure out what this is, if we're going to be going up or down or what. Okay? All right, so to complete the square here, I'm going to rewrite the function so I have it to work with. 2x squared plus y squared plus 8x minus 6y plus 20. All right, so we want to group the x terms. So 2x squared plus 8x plus something, plus y squared minus 6y plus something to complete the square, plus 20. And we need to figure out what we can fill in. So the first thing I'm going to do is I'm going to factor out this 2 right here. So this is going to give me x, well, you know what? I don't have to do that. Half of 8 divided by 2, that's going to be 4 divided by 2 is 2. So what we are going to add here is going to be 4 times 2 is going to be 8. Okay, so what that'll do is that'll allow me to factor out the 2, leaving me x squared plus 4x plus 4, which is 2 times x plus 2 squared. Right, so there's that one. Then we have y squared minus 6y, so -3 over 2 squares will be 9, so we need to add a 9 here. So plus a 9 here. I should be doing this in a different color so I can keep track of what I'm actually adding. So that's going to be y minus 3 quantity squared plus 20, but I added an 8 and a 9, so then I have to subtract that 8 and 9, so minus 17. So this is plus y minus 3 squared plus 3. Okay, so we have z equal to 2 times x plus 2 squared plus y minus 3 squared plus 3. So this is a paraboloid, and the paraboloid is opening up. Right? Okay, and at its minimum point, we have a value of 3. Oh, and how do we know what that value is? Well, you can simply plug in -2, 3. So if we plug in -2, 3, we find that z is equal to 2 times -2 plus 2 squared plus 3 minus 3 squared plus 3, which is of course 3, right? So my z value there is 3. So the minimum value is 3, and it occurs at the point -2, 3. So we have a relative min at -2, 3. Specifically, I guess I could say -2, 3, 3, and our minimum value is 3. Okay. Moving right along. We also have a second partials test. So just like we had a second derivative test, we have a second partials test. So second partials test. Okay. Goes like this. Let f have continuous second partials on an open region containing the point AB, for which f sub x of AB is 0 and fy of AB is equal to 0. Okay, so that's a whole lot of words to say that AB is a critical point. To test for relative extrema, consider the quantity d equal to the second derivative of f with respect to x, ab, times the second derivative of the second partial of f with respect to y of ab minus f of the mixed partial of ab squared. Okay. Then if d is positive and the second derivative with respect to x is also positive, then f has a relative minimum at AB. At AB. 2. If d is positive, but the second derivative with respect, the second partial with respect to x is not, if it's negative, then we have a relative maximum. At AB. Okay. 3. If d is negative, then there is a saddle point, which is neither a max nor a min, but it is a critical point. There is a saddle point at a, b, f of ab, right? So x, y, z. Okay. And 4, if we get d equal to 0, the test is inconclusive. All right, so let's use the second partials test. Let's do an example. Let's find any relative extrema of f of xy equal to negative x cubed plus 4xy minus 2y squared plus 1. Okay. So I'm going to need to know what my partials are. fx is equal to negative 3x squared plus 4x, plus 4y. Wow. Fy is going to be equal to 4x minus 4y. Okay. We need to find any critical points. Both of these are polynomials, so again, there are no xy points for which one of these does not exist, so no critical points come that way. So this is only going to work to have a critical point if 3x squared plus 4y is equal to 0 and 4x minus 4y is equal to 0. So let's solve that system. Okay. So 4y is equal to 4x, so that's helpful, because that gives me a very nice substitution here. So minus 3x squared plus 4x is equal to 0. So that implies that x times negative 3x plus 4 is equal to 0, which means x is equal to 0, or x is equal to 4/3. We'll make these come out to 0. So if that's the case, let's find out what y is. So if x is 0, that implies that y would be equal to 0 as well, because we'll plug that 0 in here and we get y is equal to 0. If x is 4/3, let's see, what do we get? If x is 4/3, we have 4 times 4/3 minus 4y is equal to 0. So y is going to be equal to 4/3. Okay. What about in the other equation? If we have negative 3 times 4/3 squared plus 4y equal to 0, we have negative 3 times 16/9 plus 4y is equal to 0. So we would get negative 3, well, 3 is going to cancel. We'll get negative 16/3 plus 4y is equal to 0, which gives us y equal to 4/3. So it's the same either way. So it looks like we have our points 0, 0. These are our critical points. 0, 0, that's a P. Doesn't look anything like a P. There we go. Critical point. 0, 0, and 4/3, 4/3. So these are critical points. So now we need to look at the second partial derivatives. So I'm going to rewrite the first partials. So we have f sub x, excuse me, is negative 3x squared plus 4y. We have f sub y is equal to 4x minus 4y. Okay. So then the partials of f sub x is going to be equal to negative 6x. F sub x y, which is equal to f sub y x, is going to be equal to 4. Then f sub y is going to be equal to negative 4. Okay, so then d is going to be equal to fxx fyy, so that's negative 6x times negative 4, minus fxy squared, so that's going to be 16. Okay, so that's going to be 24x minus 16, that's d. And we need to know if this is positive or negative given the points that we're working with. So at 0, 0, d is equal to negative 16, and f sub xx is equal to 0. But d is negative, so that tells us right away that we are dealing with a saddle point. So we have a saddle point at 0, 0. Okay. Now at 4/3, 4/3, d is going to be equal to 24 times 4/3 is going to be 32 minus 16, which is 16. So that's positive. So now we need to know what is fxx at 4/3, 4/3. So that is going to be negative 6 times x. So that's negative 6 times 4/3, which is negative 8. So we have positive 16 with a negative 8. That means we are going to have a relative max at the point 4/3, 4/3. Okay, and it just dawned on me, I didn't finish the saddle point. The saddle point is at 0, 0, and then we plug in the zeros into our original function, and what we're going to come out with then is just 1, because everything else will zero out. So our saddle point is here, and we have a relative maximum here. All right, so I'm going to wrap this one up here. As always, if you do have any questions, please let me know.